Okay, so last class we defined the dimension of a closed set, right? So the way we defined it was dimension of, in fact, an affine variety Y is how many closed sets can you embed, the longest chain of closed sets that you can embed. And then we showed, so this was the geometric definition. The algebraic one would be in terms of you look at the coordinate ring of that affine variety, or you can look at the field of fractions of the coordinate ring. What is the transcendence of that over the base field K? Right, so the transcendence degree is, we showed in theorem 1 that it's equal to the dimension definition. Any questions till now? Okay, so already at this point, with the new abstraction that we have developed, you can ask the following computational questions. So there are many computational questions that you can immediately ask. This will help you in appreciating the things we will do, more abstract things which we will be doing. So first is, as stated in the overview, if I give you a system of polynomials in the polynomial ring in n variables, so this is the input. So then the ideal defined by this system is the following ideal, right? So the ideal is basically the collection of all the polynomials generated by F1 to Fm, which is sigma ai fi, where ai is an element in the polynomial ring. So this is the relevant ideal, and you can ask the question whether this ideal, whether the zero set is empty, and which is equivalent to testing whether 1 is in the ideal. This was the content of Hilbert's Neutral-Cell-Ansatz. So this is a very practical questions. It appears in almost all the, I mean, any practical problem you can actually formulate as this. It's a very, very expressive language. Any optimization problem or anything else you can convert into polynomial system and ask whether there is a zero, which is equivalent to saying, I mean, if there is no zero, then the 1 is in the ideal. So it's a concrete computational question. I've already said before that it's NP hard, but you can still think about the best algorithms and special cases. So what you want in those special cases is a fast algorithm in time polynomial in the input parameters, which is m and the degree of fi's, and so this was finite field. So let's say fp. So log of p, and what else? N is also the number of variables. And finally, how were these fi's represented? Right. So there is some size bound. So these are all the parameters in which you would want a fast algorithm. Now, of course, in general, if you solve this, you will be solving NP hard problems. But maybe in some special cases, according to your input of interest, you could actually find a fast algorithm. So obviously, I will not solve this question here or even discuss it, but you can think about this. And if you want, you can present something as an extra talk. Second question is a slight generalization of this. So you can directly ask what is the dimension of this zero set. Okay, so dimension will be a number between -1, 0 and n. So -1 dimension means that zero set is empty, there is no root. 0 will mean that this system has finitely many roots, and 1 to n will mean that the system has infinitely many roots when we are talking about FP bar. So the zero set, we can just think of this over FP bar. Okay, so positive dimension means that there are many roots. So what is it? So is it -1 to n, the specific number you have to output, right? So the output is very small, the input is also small, but actually finding the algorithm here is hard, a fast algorithm. And similarly, you can also ask for a root in this. Okay, so actually finding a root here. So those are questions of practical interest. What else did we do? Yeah, so we defined radical. So you can ask, if I give you an ideal, how fast can you compute the radical of that ideal as a generating set? So if I was given via the generator set F1 to Fm, then obviously F1 to Fm will still be in the radical, but there may be new polynomials which were not there before. So you have to grow that generating set. Okay, this is what you have to solve. So given the ideal I via generators F1 to Fm, find these extra generating polynomials G1 to Gm prime, such that the overall thing is equal to the square root of I. Right? That's another question. And the other thing we have abstractly defined is irreducibility of a zero set, a closed set, right? So checking that. So test if Z of I is an affine variety. It's already a closed set, so you just simply have to test whether it is irreducible. If it is reducible, then you decompose it. So Z of I1 union Z of I2. Right, so these are the questions. As soon as we have the abstract concepts, you can immediately ask these questions. Generally, these are hard questions, except maybe question 4. But even that, I mean, when the number of variables is large, even that will be hard. But you can convert this into an algebraic question, which is testing whether Z of I is an affine variety is equivalent to testing whether I is a prime ideal. And decomposing the zero set of I will be like, so I will not be prime, and you have to write it as the intersection of two ideals, I1 intersection I2. So that would be factoring of an ideal. It's a factoring question. Okay, any questions? So I leave you with these computational questions and move to a more abstract kind of varieties, which is called projective varieties. So we have defined zero set, closed set, and accordingly affine variety. Now, since we are calling them affine, there has to be another term which is now projective. So we'll also look at projective varieties. And then in the future, whenever we'll say variety, it can be affine variety or projective variety. Okay, these are different things. So what is a projective variety? So in a projective variety, basically we don't distinguish a root from its multiple. Okay, so the idea is root alpha 1 to alpha n is considered the same as any multiple of it. As long as C is in the base field and non-zero. Okay, so up to non-zero constant multiples, field constant multiples, roots are considered equal. Okay, so it's basically affine variety, but then you are modding it out by an equivalence relation. So another way to say this is roots are now not points in the space but lines in the space. In the affine space. And we'll do a plus one. Or maybe not so soon, let's keep it this. So instead of these n coordinates, we'll basically lose a degree of freedom because we are only looking at lines in this space. And so this is geometrically, algebraically, we'll be studying homogeneous polynomials. That is they have equidegree monomials. Okay, so for example, x square minus xy plus y square, right? So this is a quadratic form, that's a homogeneous polynomial, but not x square plus y cube. Okay, so this is an inhomogeneous polynomial. This is not neither is it quadratic form nor a cubic form. So in affine varieties, your system may have these things, but in projective varieties, your system of polynomial equations will be like the first case, homogeneous. So in homogeneous, the key roots are basically lines, right? Because any root can be multiplied by C, it's again a root. So we basically want to consider them equal up to this multiple C. So for homogeneous F, in fact you can take homogeneous polynomial, set of homogeneous polynomials F1 to Fm. So 0 set if alpha bar is a root, then lambda times alpha bar, which is lambda alpha 1, lambda alpha 2, alpha n, right? Every coordinate scaled by lambda is again a root. For all lambda in the field, including 0, right? So in particular for a homogeneous system, 0 is always a root, and if alpha is a root, then any multiple is also a root. So we just want to remove these extra roots you are getting from 1, and for that formally we define consider the equivalence relation tilde in the affine space, removing 0. So we remove the 0 point, and everything else is like A0 dot dot an. It will be considered equivalent to a point B0 to Bn if there exists a lambda in K star such that A bar is lambda times B bar. Okay, so the thing I said before, and define the projective space, projective n space, to be this. So this is the projective n space. Okay, so note that projective n space, you will need one more dimension in the affine space because you want lines. So you need one extra degree of freedom in the affine space, and there you accept 0, all the other roots you have this equivalence relation. So mod equivalence relation simply means that many points may have the same representation, or the same point may be representing many points, the other points being lambda times B bar. So B bar represents everything that is like lambda times B bar. So these things form a equivalence class. They are in the same equivalence class. Okay. So of course you can count here. So for k equal to Fp, the affine space had how many points? P raised to n plus 1. Right, and the projective space will have, so you have to remove the 0 from there, so P raised to n plus 1 minus 1, but amongst these points not everything is distinct, right? So you have to divide by the possibilities of lambda, which is P minus 1. So that's it. Yeah, so projective n space in particular has more points than the affine n space. Okay, and it's not a power of P, it's sum of these powers. Is that clear? Another thing is, for a point in the projective n space, any A0 to An point in the equivalence class of P is called a set of homogeneous coordinates for P. And we denote it by this notation. So instead of comma, we use the separator just to signify that here what is important is the ratio. I mean, whatever is the, let's say, you can divide each of these AIs by the same lambda and it will be the same point. So let's see the projective one space over complex. So the points 2 comma 1 minus I and 1 plus I comma 1 are the same. Right, you can see this because you can multiply the second one by 1 minus I, you get the first point. So they are the same in the projective one space, but 2 comma 1 minus I and 1 comma 1 minus I, these are different. These are different points. Okay, because the ratio for the first coordinate is 2, for the second it's 1. So P raised to n is the space of all lines passing through a fixed point in the bigger affine space. Okay, so in particular we took the point 0 and we took all the lines which are passing through 0. They give you distinct points in the affine n space, but you can do the same thing for any fixed point in a to the n plus 1. Okay, that correspondence is there for lines versus projective points. Yeah, so that is the geometric picture. Now what is the algebraic analogues of what we did in affine varieties? Right, so there we used ideal, prime ideal, radical ideal. So we have to repeat all that for projective now. So let's do that quickly. So what's the algebraic analog? Or algebraic description of projective n space, and what are in particular projective varieties? What are the closed sets, open sets, and so on? So as you can already guess, we will only focus on homogeneous polynomials, right? So ideals which are generated by homogeneous polynomials, they will be the correct ideals. If there is any non-inhomogeneous I mean, if you have an ideal for which there is no homogeneous generating set, then that will not be relevant in projective variety. So ideals, as you can see, will always have, will usually have inhomogeneous elements. You don't care about that. What you care about is the generating set homogeneous. So let S be the polynomial ring in one more variable, so we call that variable x0. Define what is called a grading where SD is the degree D part of the polynomial ring. So SD is the K linear span of monomials of degree D. Okay, so grading is simply this decomposition of the vector space K vector space S, which is the polynomial ring, into these subspaces. Each is called SD for degree D. Right, so these are degree D homogeneous polynomials, and their linear combination is what a polynomial is, a general polynomial. That's all we are saying here. So these are the homogeneous parts. Think in terms of that grading to give you the homogeneous parts. and one nice property is that if you multiply two homogeneous parts, one of degree D, other of degree E, then you get D plus E. That's why it's called a grading. And with this grading, now we can define all the algebraic analogues that we had in affine variety, in the affine case. So an ideal I of this S, which now remember has one extra variable, n plus 1 variables, over the base field K, is called homogeneous I'll just shorten it to this, is called homogeneous if I has a set of homogeneous generators. Now recall again, note here that homogeneous generators does not mean that every polynomial in the ideal is homogeneous. S is as before, defined here. S is the polynomial ring with one more variable than the target. So target will be projective n space, but we have to keep an extra variable to see things algebraically. Okay, so ideal is homogeneous, then simple proposition. So an ideal I is homogeneous if and only if I follows the grading, by which I mean this. Okay, so if you look at the degree D homogeneous polynomials in the ideal for different D, then their linear span gives you the whole ideal. Okay, this is a property which is true if and only if you started with a homogeneous ideal. For inhomogeneous ideal, it is false. You can see an example maybe right here. The counter example is if you started with the ideal x1 square plus x2, then what is I intersection S1? What are the linear forms in this? There is none, right? I mean, it's only, should I call Z? Well, maybe empty is the right thing. And same is with quadratic forms. Right, so homogeneous degree 2 and homogeneous degree 1 are totally absent in this ideal. So clearly the RHS is nothing. So I is not the direct sum of or the linear span of these linear forms, quadratic forms, because everything is empty. So it happens when I is inhomogeneous. If you took homogeneous, then you can see that it's clearly true. I mean, that's a simple proof of the proposition. Second property is some product intersection and radical of homogeneous ideals is homogeneous. Okay, so homogeneous ideals behave miraculously well with all these things which we were using in the algebra for affine varieties. Okay, so ideal sum was needed for intersection of zero sets, product was needed for the union of zero sets, then intersection radical was required to have this one-to-one correspondence between varieties and ideals. So all those operators behave well on homogeneous ideals. They take homogeneous ideals to homogeneous ideals. No, yeah, that's a good question. I did not write I intersection S3. I mistakenly said it's empty. I mean, okay, you have to check that it's empty. That also will be empty, I intersection S3, S4. But even if somehow it was non-empty, it doesn't matter, because the generator of ideal I is quadratic, degree 2. So if you cannot cover degree 2, then already this condition I equal to direct sum is false. So I don't need to see I intersection S3, because good things have to happen already in degree 2, and they are not happening. Yeah, but you can never generate x1 square plus x2. It's just linear plus quadratic part, right? So S1, S2 is enough. This shows. Yeah, I think, how did I define SD? I defined it as a K linear span, so 0 is also there. Yeah, by definition 0 is there. That's fine. And example of property 2, you can see, I will not prove this proposition, this is a simple exercise. It follows pretty easily from the property above, SD times SE is in S of D plus E. From the grading it follows. But still you can see this example. So if you take x0, x1 square and x0, x1, these are the two clearly homogeneous ideals. Note that first ideal has homogeneous generators, but they are different degree, which gives you inhomogeneous polynomials like x0 plus x1 square, right? But still the ideal is called homogeneous because of the generating set. So if you add them, what do you get? You get x1 square, x0, x1 square. That I hope is the sum, yes. The second one is contained in the first. So this is the sum. If you multiply them, so product ideal, you have to multiply all the generators in every possible way. So that will give you quadratic and cubic. Well, no, cubic and biquadratic. So x0, x square, x1. And what is the intersection? So intersection is x0, x1. So in this example, you can see that all these operators, they give you homogeneous as expected. That is what you can show in general. Well, yeah, in this particular case, x0, x1 is generated by x0. It's a multiple of x0, so it's a 0 thing, modulo the first ideal. Okay, so this example is then non-trivial. At least one person is confused. Yeah, so work this out. Okay, now we can define the closed sets in this new space called the projective space, projective n space. So what are the closed sets? So you should look at subsets of this polynomial ring S that contains only homogeneous polynomials. then zeros of this given a system of homogeneous polynomials, look at the zeros and then consider them equal up to the equivalence relation. So basically points in the projective and affine n space, projective n space, Fp equal to 0. Maybe P is not a good choice in this course, maybe big P. Okay, so just like we had the zero operator, zero functor before in the affine case, in the projective case it will be same thing except points will be considered equal up to multiple by constants. Okay, so we write point P in the projective n space. Everything else is the same as you have seen before. And hence the same definition is true for ideals also. Ideal is also a subset. For homogeneous ideal I, same Zi. Use the same Zi for ideals also. Okay, so which means what? So now in the projective line, this new Z, so now will not say what, I mean, what Z is will be clear from the space you are in. So when we are in the projective space, then it is the Z corresponding to the projective space equality. So with that understanding, Z of x0 square is 0, 1. Is this clear? So the affine Z would have given you what? 0, t for every t, right? But the difference here is that since there was a duplication there, we are just putting different t's, we have now compressed all of them into one. Okay, this is just one point. So there is a difference. Sorry. Yeah, sure. Yeah, if you prefer. Yeah, so I'll abuse that because I'll set the context in the very beginning. It's a projective line, so all those things are equal. And here again similar thing will happen. This is projective Z, so will you get 0, 0? You cannot get 0, 0 because projective line that doesn't have that point. Right? 0, 0 was removed, was excluded. So all you will get is, yeah, so x0 or x1, one of these has to be 1, both can't be 0. And when one is 1, the other is plus minus 1. So I can just write these 2 points, by which I again mean 1, 1 and 1 minus 1. Okay. So you can take x0, x1 equal except 0 value, or you can take them opposite sign except the 0 value. Okay, so there are 2 points in the projective line that satisfy this. So there is a subtle thing that happens. There is a difference between affine Z and projective Z. But I hope this is natural, given the homogeneous nature of the system. Yeah, so that's the definition of closed set, as you can imagine. So Y subsets Y in the projective N space, it is called it is closed or algebraic if there exists a homogeneous T subset of the polynomial ring in n plus 1 variables such that Y is equal to zeros of T with the understanding of projective Z. And for closed Y, the complement is called open. Okay, so now we have a subtly different topology which we are moving towards. So we have defined Z, accordingly we have closed sets and open sets, and now you can see all those properties that union intersection of open is again open. And so you get Zariski topology on the projective N space. Those basic things have to be checked. So if you want, you can do it as a homework. So family of open sets in P to the N form what is called, what we'll call the Zariski topology. Okay, so the idea of a neighborhood around a point is now this abstract thing. You, for the point, you have to contain it in an open set. That's the neighborhood of a point, right? So whenever we will draw pictures like this, so point P and this is the neighborhood, this is the ball. So in reality the ball is actually a ball, but in over a finite field what we are saying is that this is some open set U, subset of P to the N, it is open, where open means this, that you have to find a system of polynomials, homogeneous polynomials T, zeros of T, take the complement. That is what U is, that contains the point P, so these are the neighborhoods. Okay, so whenever we will say in this course take a neighborhood of a point P, it will be a very, very loaded term because all these definitions go inside. Okay, and these pictures will always be wrong. So I will always trying to fool you by drawing these pictures. Hopefully you don't get fooled, or you do get fooled, whatever works. Yes. No, no, I continue with the same K. Just assume small k to be always FP bar. For this course, small k is FP bar. Well, at least till for the next 2 months, I guess, small k will just be FP bar. In the last month, when we'll prove Riemann hypothesis, there we might call small k to be FP. But theorems will always, geometric ideas will always be for FP bar. Yeah, if you don't take FP bar, then the problem is that this neighborhood business will not be good, because I mean, as we saw in examples last week, previous weeks, for a system of polynomials T, the zero set Z of T may just be empty. If your field is very small, there will be no root. So you don't want that. And so dimension etc. is defined for algebraically closed field. Yes, so now you have the natural definition of projective variety. So projective variety is an irreducible closed subset. Of the affine projective n space for some n. And maybe I say here k is equal to k bar. Just assume that. An open subset of projective variety is called quasi projective variety. Generally, whatever we will say about projective variety will be true for quasi projective variety. Only difference is between closed and open. Both are irreducible, so that will help. And dimension is defined as before. So the dimension of quasi or projective variety is defined via the chain of closed subsets. Okay, so all the geometric and the algebraic perspectives we saw before will hold with the understanding of homogeneous systems. So let's quickly see examples. Well, as I said, all the theorems will hold. So in some cases you might want to study the open set instead of the closed. Okay. Why is that? Why should it be open? Closed may not be open. Mm-hmm. Oh, in PN, oh, you are shifting to PN then, I see. Yeah, but his question was even for quasi-affine variety. Why do we define that? Okay, so let's see examples of this. Again in the projective line. So Z x0 square that we saw, this is a projective variety. What about the zero set of x0 square minus x1 square? See, zx0 square is a projective variety because it was a single point, dimension 0 and irreducible. Second one had 2 points, dimension 0, but it cannot be irreducible then, right? It factors into 2. So this is not a projective variety. It's just a projective closed set. It's not a variety. Okay, variety is a special property. Dimension of both these things is 0. These are finite objects. Let's go to the projective plane or complex. So now if you take the difference of these two, no, not these two, sorry, something else. Look at this. So, okay, what you have to remember here is that this projective plane comes from affine 3 space. Right? There are 3 variables, x0, x1, x2. So what is z of x0 square? So this x1 and x2 can be arbitrary. So there are many points. In the second one, you have already set x0, x1 to 0. So what do you do with x2? You can only set it to 1. This is a singleton. Right, so from the first one we are subtracting the second, and this is doesn't seem to be closed, but it's open. So this is a quasi projective variety. In fact, it's a curve. It's a projective curve, right? Because in 2 dimension, you have set one constraint to 0. So the remaining dimension is only 1. So it's a quasi projective curve. Yeah, you can define dimension for 0 set, or yeah, any closed set chain. Just look at the chain. Ah, I see. Yeah, you right. So you just look at the chain of varieties. Yeah. So that definition you have to change. You just look at these. In this case, they will be projective varieties, chain of projective varieties, and the last element is then not the same. Last element is the maximal projective variety sitting inside. Yeah, that's an important point. So that definition you have to change, but the thing is you want dimension to be geometrically, intuitively correct. So this is the only thing which is intuitively correct. Finitely many points, it should be called dimension 0. If you are getting by your definition dimension 1, then the definition is wrong. Intuitively it doesn't make sense. So dimension positive should always mean that there are infinitely many points, because you are in FP bar. Algebraic, I mean, if you are over complex, you should have infinitely many points for positive dimension. That's the basic intuition you have to keep in mind. Yeah, so now we can draw a nice picture of association. Recall the functors. So I of y, the ideal functor, which will take, so we are defining I, which takes some subset of points of the projective space. So maybe I should say that. So this I functor will be the ideal generated by homogeneous F in S such that for all the points that you are given, Fp is 0. Okay, so now the ideal functor will take subsets of points to an ideal, which just collects the maximal possible system, which defines your subset Y. And then to come back, so which is, yeah, that we have already defined. We already have defined the Z functor. Given a system, T, Z of T is the projective points. And the last thing is the homogeneous coordinate ring. So this will be denoted Sy. It's the polynomial ring modulo this ideal. Okay, so like we had in affine's definition A of y. So similarly we have S of y. So S is a functor here which takes an open set, which takes any subset of points to functions which are defined on top of these points. So these are S mod ideal Iy. Is this clear? And this will give you the nice picture of associations. So now you can look at the projective space, N space, and the polynomial ring n plus 1 variate. So these two, we'll think of them as associated by the dictionary of Iz functors. So a y here subset via the I functor maps to the ideal which is homogeneous, and a set of polynomials here will map via the Z functor to closed set. So closed sets are in one-to-one correspondence with what? So not homogeneous ideals, but you have to take the radical. Again, this is a version of Hilbert's Nudel-Selensatz, identical to what we proved before. So radical homogeneous ideal. So in a way you can say that these radical homogeneous ideals, they are completely characterized by the zeros, which is the closed set Y. What? Yeah, that was a proposition you have to prove. So projective varieties will be in one-to-one association with homogeneous prime ideals. And single point will be in one-to-one association with maximal prime, which is a maximal ideal. So these are one-to-one. Okay, so these I and Z functors, they behave best on the definitions we have given: closed set and projective variety. One explicit way to study projective varieties is by reducing it to affine varieties. So we call it affine cover. So we can study projective or general projective N space by affine coverings. So this happens because, so let's go to the projective plane over complex and the zero set that we had. So we can, this is what we were doing also when we were trying to find the roots, the zeros. So what we think of is there are three variables x0, x1, x2 in the affine 3 space, and we cannot have all three 0 equal to 0. So we set x0 to 1, then we set x1 to 1, and then we set x2 to 1. Right? So basically those are the three affine parts of this projective 0 set. Okay. I mean, you take a maximal ideal. Yeah, if it is inhomogeneous, then you reject, because here I need homogeneous. Yeah, but I want both the conditions, homogeneous and maximal. I thought this is a symmetric. It's not symmetric. Yeah, I want an ideal which is both homogeneous and I see. I mean, amongst homogeneous ideals, I want maximal. So then should I do that for the prime case also? Yeah, so that's a bit asymmetric. Amongst homogeneous, you get the maximal. That's the point. Yes, so here you just follow the algorithm you use to find the points, right? So you set x0 to 1. When you set x0 to 1, then x1 has two possibilities, plus minus 1. Third parameter is free. So any complex number. So this you can see as an affine closed set. That's the first part. But this doesn't give you everything. In fact, disjoint. There are other things remaining, right? Which is you are now allowed to set x0 to now you can allow you can set x0 to 0, so x1 will also be 0. So you can set both of them 0 because you have a third parameter which is free. So that is then 1. Right? So you can, so what we will do now is we'll just look at this as two affines covering the projective closed set. The first one is the first affine component, and second is the second affine component. The union of this we call an affine cover. So let's just formalize this simple thing. Is this clear? Example. So that's a proposition. So P raised to n has an open covering via n plus 1 affine n spaces So this is just you look at the following closed set. A0 to AN such that AI is not equal to 0. And this you do for all I. Okay, so I have defined U0, U1 dot dot UN. where for a particular I just say that AI is not equal to 0. Now, since AI is not equal to 0, I can as well normalize this by AI. I make AI 1. Right? So, these are the positions of 1 that you get, n plus 1 positions, and that will cover all possible points in the projective n space. So, that is what I write. Pn is union of ui I 0 to n. And ui is a to the n. Yeah, technically I should say homeomorphic, but that is something I have not defined. So, ui is essentially a raised to n via the following map, and that is a nice map. It is phi I ui to a to the n. It does what? It sends a0 to an, e0 dot dot an to, as I said, you just divide by ai. Sorry, this has to be omitted. Okay, so from n plus 1 coordinates, you go to n coordinates. You just omit this ai by ai thing, which is 1. So, you go from a0 to ai minus 1 and then go from ai plus 1 to an. You just reduce one coordinate. So, that is a well defined map from ui to a to the n, and you can see that in the image you have the whole affine n space, and in the domain of course you have this ui, which is which you can see what it is. This map is what is called homeomorphism, because you can see, you can prove that pre-image of open set is open. In fact, no, it is stronger than that. Open sets of ui and open sets of a to the n, they are in one-to-one correspondence. Okay, so when this happens, then you are sure that the Zariski topology, the geometry is being completely preserved. So, in that sense, ui we can say is a to the n. Okay, it is just a relabeling. Geometrically, it is the full affine n space. So, this together with the cover union of ui being p raised to n, we have shown, we have basically decomposed p to the n into open subsets, each of which is the affine n space. Are these ui's disjoint? I mean, there is no way to compare them, right, because they are, I mean, the coordinates that you are dropping are coming from different places. So, you can't really compare. No, you can, sorry, the embedding of ui is in the same n plus 1, a0 to an coordinates. Yeah, so you can ask actually then this question, are these disjoint or not? Yeah, so this is not a disjoint cover, so points actually overlap. Point may be present in many uis, which is why you don't get the correct count. You cannot just say that n plus 1 times the size of ui is equal to the size of p to the n. Okay, there is a heavy overlap. These things are overlapping. So cover doesn't mean that it's a disjoint cover. It just means that I have a way to like look at neighborhoods which look like the whole affine space. Okay, so we have patched together different affine spaces. This patching is a very important geometric construction. It can be taken to a insane level of abstraction, which we will not do in this course. So this property of p raised to n is inherited by all projective varieties and quasi-projective varieties. So this inheritance means that what we did with p raised to n, we decomposed into these affine n space patches. We can do the same thing for a projective variety, decomposing it into affine varieties. And that is now straightforward. So what you do is, for projective variety y, write y as union of same thing like before, I equal to 0 to n, intersect with ui. Okay, in that big projective n space, you have these patches ui's. So you just intersect your projective variety with that patch. You will get possibly a smaller patch, which is a subset of y. Yeah, and that's an affine variety. So n plus 1 affine varieties now cover your projective variety. Is that clear? Okay, so that is it. Next time what we will do is, we will, so now we have defined varieties of all types, affine varieties, projective varieties, quasi-affine, quasi-projective. What we need to do next is we want to compare two varieties. So we will do morphisms next time.